Solubility rules simplified our classification of ionic compounds as soluble or insoluble. However, it's important to note that this classification doesn't tell the whole story, as equilibrium plays a crucial role. That is, any compound labeled as insoluble is actually slightly soluble, with the assumption that the small amount that dissolves fully dissociates into ions, that are cations and anions. This leads to a saturated solution in equilibrium between the solid solute and its aqueous ion. PbF2 nightcrawler, or lead-2 nightcrawler, is an example of a slightly soluble ionic compound. Now, nightcrawler can teleport, and when lead ions and fluorinated ions meet, they swiftly create a white, slightly soluble solid that teleports out of solution, right? And so that's how I'm making that connection. Of course, this reaction here is a balanced equation, and as you can see, it is in equilibrium. So we have the PbF2 solid in equilibrium to form Pb2 plus and 2F minus anion. And of course, everything is balanced. Now, anytime you have a reaction that's going to be in equilibrium, you can create a reaction quotient, that is QC, and that's going to equal your products divided by your reactant. So that is our Pb2 plus multiplied by F minus squared divided by PbF2. Now, since PbF2 is a solid, it's going to be considered a pure solid, just like water was considered a pure liquid, and therefore it's going to equal 1. So anytime you're basically taking away a species and just putting 1, you're creating a brand new expression called the QSP. So the QC, or reaction quotient, which is what we're used to when it comes to equilibrium, is going to have all your products or your reactants. Once we again take our solid as 1, then we're going to form our new variable here, which is our QSP, and the QSP is simply going to be our ions that we have. The QSP is called the ion product expression, and this is going to be for any slightly soluble ionic compound. So when you're writing your QSP, you must have your cation and, of course, your anion. Now, of course, we're squaring this here because that's based on the stoichiometry, or the amounts that are in front of each of the species in the balanced chemical equation. So at equilibrium, when the solution is saturated, our QSP value is going to be transformed into our equilibrium expression value, which is KSP. And KSP is going to stand for solubility product constant. It's still going to equal Pb2 plus multiplied by F minus squared, because it's still going to be based on the equilibrium balanced equation here, okay, folks? And we usually write KSP expressions, but we can use Q and K and compare them both to help us with precipitation, as we'll see later on. Okay, folks, so we're back at the Avengers compound so that we can get some, experience writing out these KSP expressions. So this question says, write the ion product expression at equilibrium. So we know the ion product expression is QSP, but at equilibrium, we're looking for KSP, okay? They want us to write the KSP expression for each compound. So what does that mean? That means we must first read what we have here, letters A through D. And as you can see, we're not given formulas, we're given nomenclature. So we definitely have to get the formulas of our ionic compounds here. And as we saw before, we definitely need to write a balanced reaction. And then from that balanced reaction, we can go ahead and get our KSP values. Sometimes instead of just saying like a balanced chemical reaction, you may also hear the expression, write an equation for a saturated solution. That's still like saying write an equation at equilibrium. Okay, folks? So let's get the nomenclature down first. Again, we're talking about an ionic compound, so we must have a cation and anion. Magnesium is group 2, so you know it's going to be a cation of Mg2+, and then carbonate is a polyatomic ion, and so we're going to get MgCO3 here. Next, we have iron 2 hydride. It already tells us that iron is going to be Fe2+, and hydroxide is going to be OH-, so we're going to get FeOH2. And remember, we're producing all solids here, okay? Next, we have calcium, which is group 2, and then the polyatomic ion phosphate, which is PO43-. That's going to give us Ca3PO42, and again, this is a solid. Finally, we have silver sulfide. So silver is Ag+, and then we have sulfide, which is S2-, and that's going to give us Ag2S, okay? And this is also a solid. Now, the next thing is to write the expression, or of course, the equation for the saturated solution. So for letter A, we had MgCO3 solid. That's going to be in equilibrium to form the ions that we already have written, which is pretty cool. So we're just going to use the ions we have, okay? Mg2+ aqueous, plus CO3 2 minus aqueous. Now the KSP expression for this is going to be Mg2 plus and CO3 2 minus. Of course, this is going to equal 1, so we do not write it when it comes to our SP expressions here. Okay, folks? Let's go on to letter B. For letter B, we have FeOH2 solid in equilibrium to form Fe2 plus and 2 OH minuses so that we can have everything balanced. Therefore, the KSP expression is going to be simply the products here, Fe2 plus and then OH minus raised to a power of 2. For letter C, we have Ca3PO4 in equilibrium to form 3 Ca2 plus and 2 PO4 3 minuses. Of course, everything's already balanced here. Therefore, the KSP expression is going to be Ca2 plus raised to a power of 3 and PO4 3 minus raised to a power of 2. And finally, for letter D, we have Ag2S, which is going to be in solid, is going to be in equilibrium to form 2 Ag plus and S2 minus. The KSP expression for this is therefore going to be Ag plus raised to a power of 2, and then of course S2 minus. Okay, folks? So you want to make sure that you're able to write out these expressions because you have to use these when we get into calculations.